algebra expert, what you'll find out is that you will keep learning your algebra as we go through the algebra of trigonometry. So sort of just relax, it's okay. But the problems that you did on that preview, they were well done, so that's a good sign. Okay, I do expect that you understand the basics of algebra, and then I'll show you how to apply it to trigonometry. Now, the unit is called Trig Identities. It is the Trig Identity unit. What's an identity? What's an identity? Well, glad you asked. If you think about the word identity kind of in English class, well, it kind of has the same meaning in math class, okay? Because an identity is who you are. So a trig identity, or an identity in math, is what something is. In other words, statements of equality, when something is equal. So again, an identity is really just a statement about something being equal. Now, identities are all around us. To say that 2 plus 2 equals 4 is an identity. Obviously, it's pretty easy. But in the same manner, we will have statements using sine and cosine that will say what something equals. And I always like to add this little emphasis, no matter what. Okay, there'll be some statements we create that are identities, in other words, that are equal. And there, you might even say to yourself, really? That's equal? Yep, no matter what. Now, believe it or not, you already know some trig identities. They've been part of kind of our study of trigonometry almost since day one, almost. And so let's do a little pretest, just kind of get you guys thinking about identities. We'll do a little true-false. You can just participate. I mean, you can write it down if you want, but our main thing is make sure you're participating. So, is that an identity? Is secant equal to 1 over sine? Okay. As many of you said correctly on the past test, no, it is not. But what is equal to 1 over sine? Cosecant. So take a look at that statement, because that is true, which means that is an identity. Okay, so again, the second statement up there, that's an identity. We actually will put that in our notes by the end of the period. But you already know it, or at least you've seen it. Okay, identities, statements of equality. You think tangent equals sine over cosine? Now this one I've never outright shown you, but if you think about sine, you should say it's y, and if you think about cosine, you should say it's x. So is tangent equal to y over x? Yeah, so if you were kind of like, it seems like it's true, it is. It's a true identity. Now take a look at this. Before you say, oh, I've never seen that before, take a look at the statement up above. We already said it's true. So would this statement be true? Why is it true? Why is it true?
I know that tangent is y over x and cosine x, but you won't put it together, you'll find y.
Good. There's definitely the idea of multiplying together. Sometimes people say they just multiplied cosine to the other side. Same idea. But the point behind this is that if you have something that's true, you can then create another true statement if you just use algebra. If you just use algebra. This is kind of different. It says sine plus cosine equals 2. Well, honestly, there's no reason that you would know or not know this. It happens to be false. But the real reason I put it up is so I could show you that there is going to be a true identity. There is going to be a true identity that uses sine plus cosine. And of course, it's going to come from, well, I shouldn't say of course, but can you guess that it would come from the unit circle. Now, all I'm doing here is just getting your attention that there is an identity that uses sine plus cosine. But what we need to do is we need to explore the unit circle and the Pythagorean theorem. Now, the little paper that you grabbed on your way in, when you're ready to kind of transition to that, that is meant to help us discover this identity. Okay, now to discover this identity and to have a little fun with it, I like to say that we're going to try to make the Pythagorean theorem talk. We're going to make the Pythagorean theorem talk. Now, if the Pythagorean theorem could talk, what would it say? Well, you're going to find out that it's going to say an identity. Okay, now look at the little paper that you grabbed on your way in. It's got a simple diagram that is yet to be filled in, and that's for you. Okay, we're going to do kind of a little activity with this. I'm going to encourage you to fill in anything that you think would be true about that diagram. And I'm going to roam around, if that's all right. And if I see you do something, if I see you fill something on that diagram that's worth repeating, we're going to blow a little horn. We're going to get a little excited. And then I'll ask you to maybe share, what did you do? So you're looking at that diagram, and just simply, what's anything that you could add to that diagram that would be true? All right, now I stopped over here at Grace, and there's something that you did. There's actually a couple things, but if you can just maybe share what you did here.
I drew a triangle going down to like the x-axis.
So she drew a triangle going down to the x-axis from that point. Now, just so everybody's drawing the same triangle, it's like the one you've seen many, many times. What else is true about that diagram? What else is true? You're like, I don't know. What's true here? Well, so I stop here at Anna. You have something that's true about the legs of the triangle.
I said we know that the y part of the triangle would be equivalent to sine of theta, and then the x part of the triangle would be equivalent to cosine theta.
So she labeled the legs of the triangle, the y part as sine of theta, the x leg as cosine of theta. That's a good one. That's a good one. It is definitely true.
Everyone has already. Sorry.
What else is true about that diagram?
That's all.
Okay. Ryan's got something up here.
The hypotenuse is equal to 1.
The hypotenuse is equal to 1. It's getting close. The Pythagorean theorem, if it could talk, what would it say? If the Pythagorean theorem could talk, what would it say about this diagram? It's getting ready to talk. Speak. Speak. It's starting to talk. It's actually starting to move around the room. There are some right answers. I just want to give people a chance to think about it. The Pythagorean theorem, if it could talk, what would it say? Like, I don't know. This is weird. What does it say? Starting to get it. There's some more right answers. Ta-da! Go ahead. We're going to let it talk now, but I want to make sure everybody knows what it's going to say. Can you tell us, Alyssa, what did you say the Pythagorean theorem would say about this diagram?
Cosine of theta plus sine of theta equals 1.
That's not quite what you wrote.
Well, cosine of theta squared plus sine of theta squared equals 1 squared.
Cosine of theta squared plus sine of theta squared equals 1. It's the Pythagorean theorem of the unit circle. And ladies and gentlemen, it is the Pythagorean identity. It's the Pythagorean identity. Normally, it rattles off our tongues as sine squared plus cosine squared equals 1. Okay? So the placement of the square is kind of new for you guys, but I want you to see it. I want you to hear it. It's what the Pythagorean theorem would say. It says sine squared plus cosine squared equals 1. And you can put that in that little call out box if you want, or however you're going to make note of this amazing statement. It is actually quite a thing of beauty, the Pythagorean identity. As I look around the world, there's many things that catch my eye. One of them is my wonderful wife that I actually met in high school. But a close runner-up is the Pythagorean identity. Sine squared plus cosine squared equals 1. Okay, it is a statement of beauty. In fact, it's so beautiful that if you ever see me like out and about, like maybe you see me at Lowe's shopping for like some lumber maybe or tools, if you see me there, I want you to say, Miss Naylor, sine squared plus cosine squared equals 1. I actually had somebody do that once. I was kind of like, huh? Because I was not in school mode. But seriously, it's something I want you to remember. And maybe it too catches your eye as a thing of beauty. Okay, it's the Pythagorean identity. Now, just so you understand why I'm so excited about this, this is always true, like no matter what. You say, what do you mean no matter what? Well, technically, as most of you wrote on your paper, any angle, because x is an angle. So what this is really saying is that like sine squared of any angle plus cosine squared of any angle will always equal 1. Let me show you what I mean by this. Okay, now this is just kind of like a little numeric, this is just a little numeric observation about this identity. And it also has given me an opportunity to show you like how to type in the square, because a lot of times kids are like, what's up with this square thing? And it's something we'll keep working on. It's not a big deal. You'll understand it. But if I want to do like sine of some angle squared, you actually still type it in this way, because you can't get the square. You can't get the square like beside the trig function. Not on a calculator, not on Desmos, not on a computer. So, for example, we do the sine of 30 squared. Now, it's not 30 squared, it's the sine of 30 squared. But the calculator does it correctly. Now, check this out. I typed in any angle, and guess what it comes out to? 1. You say, that's just because you typed in 30. Well, I don't know. What's like a really random angle? 17. Ooh. Sine squared of 17 plus cosine squared of 17 equals 1. Okay, now the reason for this is because of what you just did on that little diagram. If you look at that little diagram, you proved that it always equals 1. Okay, with any theta. With any theta. Okay, now that's Pythagorean identity. And what we're going to do now is kind of transition maybe a little more to your notes, so that I can continue to show you like what's up with identities. And what we're going to do is start with this identity, we're going to start with this Pythagorean identity, but you'll find out real quickly that it allows us to create more identities. I'll show you what I mean. You'll catch on. We're actually going to be making a couple different groups of identities in the next 15 minutes. Okay, now I hope that even when you write that, and you'll write it many times over the next couple weeks, but as you write that, you realize that that comes from our little observation with the unit circle, a triangle, and the Pythagorean theorem. But now what we're going to do is we're going to observe some algebra, and you're going to feel like you kind of have walked back into algebra class again in the next few weeks. It doesn't have to be a bad thing. But with a little bit of algebra, I want to suggest that we could divide everything in this equation. Now you're like, wait a minute, why are you doing that? Well, because I'm going to show you something. But before you just ask, why am I doing that? I want you to agree I can do that. You can divide everything in an equation by rules of algebra. And so what if we divide by cosine squared? Now don't get too hung up on why are you doing that, because you're going to find out in about 30 seconds. But make sure you say, I'm allowed to do that. Because again, I can divide anything I want as long as I do it to every part of the equation. Okay, so we're going to divide everything by cosine squared. Now, some of this is new, but maybe you can make some educated thoughts, and maybe you're still just kind of listening. But here I have sine squared over cosine squared. Now, a few minutes ago, we had sine over cosine, and more than a few of you said that equals tangent. So I take a guess what sine squared over cosine squared equals? Well, it would equal tangent squared. It would equal tangent squared. Now here's one that everyone can answer. Cosine squared over cosine squared. Numerator over denominator is going to cancel to be 1. We're making a new identity. I know, it's also kind of neat. 1 over cosine squared. Now, a few moments ago, we looked at something on the screen that said 1 over, actually it was 1 over sine. But here's 1 over cosine squared. Secant squared. Good. Secant squared. What is that? What is tangent squared plus 1 equals secant squared? Well, it's another Pythagorean identity. Just take it in a moment. It's another Pythagorean identity. It's true no matter what. It came from, I erased it already, but it came from dividing everything in the original identity by cosine squared. Feel like you could provide some suggestion on what to divide by? Like maybe divide everything by sine squared? Maybe you're the type of student that you want to predict what happens here. Maybe you still just want to wait for me, but you're dividing everything by sine squared. That is definitely legal. So what do you get? Of course, sine squared over sine squared is 1. How about cosine squared over sine squared? That's kind of new, but it is similar to, in fact, it's the reciprocal of, now that would be the reciprocal of a tangent squared, which we call cotangent squared. So cosine squared over sine squared is cotangent squared. And then 1 over sine squared, it's pronounced cosecant squared. That's another Pythagorean identity. Kind of neat how, though, everything originated still from the thing of beauty. Okay. Now, that was using algebra. It was a little dividing algebra. The truth is, we can also do a little bit of adding, subtracting algebra. Okay. Now, if this thing's an equation, then there's no reason I can't add or subtract something to the other side. And if I would subtract cosine squared to the other side, then I would get a statement that would say sine squared equals 1 minus cosine squared. I hope that you look at that statement and you understand that it's really the original statement. It just has the cosine squared undergone a little algebra, a little subtracting. And again, if you're saying, well, why? You'll find out the reason why is that we want to be able to recognize these kinds of statements. Okay? And we'll use them throughout the chapter. But right now, we just want to be able to recognize that they're true. Subtracting cosine squared didn't necessarily wasn't anything special, because I could subtract sine squared. Maybe you're already saying, well, couldn't you just do any algebra? Yes, you could do any algebra. As long as it's legal, you would get another derivation. Okay? Just kind of showing you the popular ones. This one, we're just going to do one maneuver, although we could move things around all we want. If we move tangent squared, we kind of end up with an interesting looking identity, because it says secant squared minus tangent squared equals 1. Interesting. It's another identity that equals 1. Secant squared minus tangent squared. Notice the way that I wrote it. It's pretty common to see it written as secant squared minus tangent squared first, and then it equals 1. And we could do the same thing with this last one. Basically make it equal 1 by moving cotangent squared. Move cotangent squared over here. So we have a minus cotangent squared, which equals 1. It's actually cosecant squared minus cotangent squared equals 1. All right, those are the Pythagorean identities. All kinds of fun and games and math problems that we'll do with these identities. I'm going to show you another category. They are the reciprocal identities. The reciprocal identities. Okay, and probably not a big surprise that they all will involve reciprocals. But let me kind of help us get started. Just like we had up on the true-false, cosecant is the same as 1 over sine. So those are reciprocals of each other. Cosecant is the same as 1 over sine. But it's very similar. In fact, it's 100% equivalent to say that sine is 1 over cosecant. I hope that you look at both those statements and realize that they're saying the same thing, and that is that cosecant and sine are reciprocals. If you do a little bit of algebra, you could argue that we multiplied sine over to this side, and we divided cosecant over to this side. Those little yellow arrows are just some basic algebra maneuver. But we also would have the secant reciprocal identity, secant equaling 1 over cosine. And then cosine, of course, is 1 over secant. Now, sometimes at a moment like this, students start to see like X's and Y's kind of dancing around. Almost like what Julie was talking about. Well, really what she was talking about, that all these statements really refer back to X and Y or R, X, Y, R. And so you could think of any of these statements as X, Y's, and R's to help you understand that they are true. And then we can go to the cotangent reciprocal of tangent. So cotangent is 1 over tangent. So tangent, of course, is the reciprocal of cotangent. Basically the same thing, just solved the other way. And those are the reciprocal identities. Today's lesson was to introduce to you these identities, have a little fun discovering this, start to show you some other ones, and then you got to come back the next day and we'll figure out what to do with these. So if you're kind of like, what can we do? You got to come back. Today I'm just showing you that these are true. The last batch we'll do today are the quotient identities. Now, quotient's a fancy math word for fractions. Although there's some fractions that are already on the board, those are more of reciprocal type. These fractions, well, they fit into the quotient identities. As you can see, we have a quotient. We have tangent equaling sine over cosine. Again, it's kind of like x and y. Tangent is y over x. Sine is y. Cosine is x. Okay, that's why these identities, they've been in the background for some of the math that we've been doing since the beginning. If you multiply cosine over to the other side, if you multiply it over, good algebra, you would get a variation. You would get a variation of this identity. You would get that sine equals tangent times cosine. Just a little side note here, that's still the quotient identity. Although that's a product, just to be clear, that's a product. It still technically is the quotient identity because of where it originated. And then there's one other quotient identity. It's the cotangent. And maybe you want to just think about what would happen if you would multiply. If you would multiply sine to the other side, you would get a cosine equaling cotangent times sine, which is another quotient identity. The algebra of trigonometry. I'm not sure what you thought, but I hope that you give it a good run. Okay, it'll definitely be a unique chapter. One thing that's definitely true, if I could bring in like a guest speaker from like last year that's now in calculus this year, is how much you'll use these ideas as you move forward. Okay, so glad you're here. Sign on for the next number of weeks as we walk through this together.
That original identity, sine squared plus cosine squared, if you doubled them, what do you get to?
Yeah, good. If you doubled them, if you basically did anything to them that was legal. So, yeah, you might remember I had a true false up there. That technically would be what would be true. It would be 2 sine squareds plus 2 cosine squareds would equal 2. It's very good. It's actually kind of where we're going to go tomorrow, which is starting to kind of adapt these and start to use them. Make sure you take one last look. Let me erase these 2's, Ryan. Take one last look at this thing of beauty, okay? Because I definitely want you to know that sine squared plus cosine squared equals 1. Now listen, this is that